Okay, good morning, everybody. One thing I wanted to mention, on the end table here, if you'd like a certificate to hang on your wall, they asked the companies to provide that, so we provided one that says Zero Zone. So feel free to take one along, hang it on your wall. If you want the credit through the NASRC, you still need to be doing that code. This is just a piece of paper on the wall for you there. So with that, a little information about myself before I get started here. So I currently work for Zero Zone. I'm the Director of Regulatory Compliance and Refrigeration Technology. And in that role, what I do is I do work with sort of more of the large-scale regulatory issues, right? Work with the DOE, EPA, UL type of things. Kind of make sure our company's positioned correctly to meet the codes and also to influence the codes, how it affects the industry and our company particularly. Also, I do special projects, special engineering projects, support a couple of our key customers, and then do training on CO2 we do classes once a month at our facility with that as well. Before that, I started out a while ago, spent 10 years at Vilter Manufacturing. You know, Vilter is more of an industrial application, did some ammonia type things with them. They also did Freon at the time, so I have a sort of an industrial background. It's been a while. Then I spent the next 20 years, I was the engineering manager for our case division, where we made display cases. So last 7, 8 years, 9 years, I've been in Director of Regulatory Compliance and Refrigeration Technology. So a little bit, what we're going to talk about today, give you a little bit background on our company, a couple slides on that. Then we're going to be talking about safety, because safety is important, right? Safety affects you, it doesn't really affect me unless I'm standing there next to you with that. We'll also then talk about CO2 components, again making sure we all have the same understanding of the components used in the system, because some of those are going to be what we're going to talk about then with how the high pressure valve controls and what it's doing. So we need to know about components to kind of get to the core. And we'll look at the pressure enthalpy diagram with that. Then lastly, we'll finish up, look at some CO2 system type issues, or not issues, but some of the safety devices that are put into CO2 systems, and look at some piping and instrumentation diagrams. Again, something you should be familiar with if you're working on these systems, and asking for when you're working on a system. So anyhow, what are our learning objectives? First, we want to understand the safety concerns. So we'll talk about CO2, working with CO2 and proper equipment to wear with it. Remember, CO2 is a refrigerant. It's under pressure and it's under temperature. If you're currently working with refrigerants, it's under pressure and it's under temperature, right? It's hot gas. If you get liquid refrigerant on you, spill some on you, it's cold. So CO2, same thing, just a little bit more amplified, right? Higher pressures, colder temperatures. Then we're going to spend that time talking about that high pressure expansion valve and how that works with system efficiency. So you should be able to go home and know, well, I know why that valve's going up in pressure on a hot day. I know why that set point's moving. I know the reason why. Not what they told me it should go up, but I understand why, what it's doing with flash gas. And then lastly, some of the designs to protect the system from overpressurization. And that gets really into the service aspects you guys do. So a little bit about Zero Zone. We have 2 divisions. We have a display case division and a refrigeration systems division. Display cases, we build those in Wisconsin, just west of Milwaukee. Refrigeration systems, we build those in northwest corner of Minneapolis, and we have a plant in Dyersville, Iowa. That's where the Field of Dreams was filmed, so that's its claim to fame. So with that, systems, pretty much custom engineering, custom design systems. Indoor systems, outdoor systems, have the system sit on a roof, goes out on a flatbed, it's fully enclosed. Working with different refrigerants, we do ammonia, do HFC refrigerants, we do a lot of different CO2 refrigerants. Our CO2 line of equipment now, I have underneath the brand Genesis type thing, so information with that. Then with the display cases, do cases with doors, a lot of cases with doors, that's kind of our primary. Do open cases, and again, the cases are going to have HFC refrigerants, and of course they're all going to have the capability to run with CO2. And we're seeing a slow movement towards CO2, what we obviously we sell what people want to buy. slow movement towards CO2, we expect that'll be pushing up as regulations take place, which is why, of course, we do the training, get you guys ready to be able to operate them. So on to safety. So again, refrigerant CO2, you need to respect it. You need to respect the pressures it operates underneath. We need to respect the temperatures. But a lot of the risks are the same as you have with other refrigerants as well. All refrigerants can be fatal as they displace the air in the room. All right, so if we have any refrigerant today, if we get a big leak and we're in a small room, we need to get out of the room. We're going to run out of oxygen. CO2, we breathe CO2, but again, if it's all a full concentration of CO2, we're going to run out of it. It's not going to turn out well. If we're doing ammonia, with ammonia, we're going to it's also going to be a toxin to us. So ammonia, you usually don't wind up dying because you don't have any air. With ammonia, typically you're going to smell the ammonia, you're going to leave the room before you get asphyxiated with it. But it can be a hazard to your skin. The other thing you have with CO2, it's denser. All right, all the refrigerants typically are denser, except for ammonia, denser than air. So when they get released, they go to the floor. If you start succumbing to being asphyxiated, you hit the deck. Where you land? On the floor. Where's a higher concentration of gas? On the floor, right? So that's kind of a double hit. So you really want to avoid that risk. Other thing about CO2, which makes it unique compared to other refrigerants, it also has a narcotic capability to it. So if you start getting succumbing to CO2, you can lose your ability to think and reason. So we had one of our engineers, when we were talking about this, said he had a leak in his furnace, so he's getting carbon monoxide in his home, and he said it was the weirdest thing. He's sitting there and he's going, this isn't going right. I need to be getting me and my family out the door. But he said it really took a lot of concentration to make that happen. And we think that was related to this narcotic effect. So if you start having that, you don't want to wait till the last minute because, depending on your mind, you may have a hard time understanding where the door is, how to get down, get up a staircase, do whatever. So the advantage, though, with CO2, as we get CO2 levels in our bloodstream, our heartbeat and our breathing starts speeding up. So we have kind of a self-monitor. So again, you're working with CO2, you got to respect it. If you start noticing, boy, you're breathing pretty fast, and you didn't really do any extra work, you're only turning a wrench, you're just standing there watching the controls, and you're noticing your breath or your heartbeat picking up, you really want to start looking for the door, go out and get some fresh air, right? You don't want to look for the leak until you get some fresh air with that. So they have some numbers on that as you start going. As the CO2 gets elevated in the air, you wind up having your breathing starts picking up. If you get up to 18-20%, you start looking at having a stroke with that. So again, CO2, like all refrigerants, can be bad, but pay attention to yourself when you're working in a room. Safety placards, so if you got some trucks, you wind up with a 2 in health just because it's an asphyxiant. You wind up with the same thing, though, if you have 404, again, it's an asphyxiant, you wind up with a 2. 404 gets a 1 for flammability. 404 can burn, but the flame won't spread. So you can, if you try hard enough, you can get 404 lit up, but it doesn't spread, so it's not considered I guess, a flammable gas in the refrigeration world, but from a DOT standpoint, it has some flammability to it. So a big thing comes down to personal protection. What are you guys doing to protect yourself when you're on a job site? Again, respecting our refrigerant with that. So you do have higher pressures. If you have a leak, there's more likelihood you can get a leak and you can spray oil across the room or near your body compared to other refrigerants, just with the higher pressure. So you should be wearing it, and a lot of these aren't unique. Safety glasses. Then when I'm out on job sites, rarely do I see people with safety glasses on. Technicians, I don't know, for some reason don't think they need safety glasses, but you should have safety glasses on when you're working in any type of situation, cutting the grass at home, working on a rack, you should have your safety glasses on. You only have 2 eyes. If you lose one, it might be a little embarrassing to go home to, besides the pain, embarrassing to the family. Why'd you lose your eye? Well, I didn't think I needed safety glasses, sorry. Not such a good thing. CO2, you may also want to look at face shields depending on what you're working on. Got a photo there. You guys ever hear of using CO2 as a blasting agent? Instead of sandblasting, you blast with CO2? Somebody in the last one heard it. The advantage you have is that you don't have to clean up the sand, right? So it's kind of a cleaner blasting agent. But what you want to take away from that, it is a blasting agent. So if you had a leak, severe leak right by you, and you're getting hit with one, it'd be cold, frostbite your skin. Two, it could damage your skin with that. So that's where, again, thinking face shields. Long sleeves, gloves to prevent that. The story on that, of course, the case plant, we'd use CO2 to make vapor to look at air curtains and cases. And it's kind of nice because the room doesn't smell like a smoke pen. So a lot of times you get a bag of CO2 chunks, add a cup with water in it, you pick up a chunk of CO2, a cube, and drop it in there. You know, and of course gloves aren't there, you're not looking for it. Then you get home at night and you feel the tingling in your fingers, right? So I got frostbite. And all I was doing at that point in time, you know, I'm picking it up and it's got to be a second or less before I'm dropping it. But that cold temperature, CO2, dry ice is going to be at around minus 100. And that 1 second was enough to give me the tinglies later on in the day with those fingers on it. So you need to be aware of it. Same thing then comes into play if you have snow in something you're working on. So if you're working on changing a filter dryer or a suction dryer, you had some liquid in there, it flashed off to snow. What don't you want to be doing with your bare hand? You don't want to be cleaning the snow out with your bare hand, right? You want to be putting some gloves on, using a tool or something like that. Otherwise, later on, you might have frostbite on your hand. Depends how much you get on. It could be bad or just the tinglies with that. Other thing you have to be aware of in working with CO2, a lot of the other talks have been talking about it, I'm sure. If you trap CO2 liquid in a line, the pressure rises really fast. And fast enough that, or say high enough, as it warms up, that you could easily break the line or cause the lines to swell. So when you're working with CO2, you do not want to have a liquid line, shut valves on it and trap liquid between it. If you have a filter dryer, it's full of liquid, that's what it's supposed to be. You don't want to close the valves and then walk off and do something else. It's not going to turn out well. You might have something broken you have to watch with. So that's something that, you know, technicians, we need to be aware of. We don't want to bottle that up. Same thing can happen if you have liquid and vapor, but not as dramatically. Liquid and vapor, as long as there's liquid and vapor present, it's going to continue to follow its pressure temperature chart, and the pressures are going to rise, get you up over 1,000 pounds. So again, possible damage to the equipment or the piping, or you could have a relief valve release CO2, and then you have to go bring a bottle over, recharge it. When you depressurize the line, you drop that down. CO2, you get below 60 psi, and you generate dry ice. That's why you have dry ice when you go to the store. It sits on the table. We usually talk about it in training, set it at 100 pounds because it's an easy to remember number. When you drop that liquid down inside a pipe below 100 pounds pressure, 60 the actual number, it will instantly convert that liquid into dry ice. So depending on what you're doing, where you drop the pressure down, you could potentially get a plug of dry ice in a liquid line. Then you got to wait for it to kind of warm up and melt. So it's something just to be aware of, which you have to work with that. Other one you have with CO2 is you have a lot of safety valves, and depending on what's going on, an upset in the system, you might have the likelihood that a safety valve is going to release. Who in the room hasn't had a safety valve release near them? Everybody's had that? Okay. If you haven't, they can be kind of loud. The bigger the volume of the vessel, typically the louder they are with that. So you have to be aware of again, everything. A lot of this points back to you guys. If you're a real jumpy person, you got to be thinking about that. Where you're standing, where's your body position as it relates to a safety relief valve. Because if one goes off, you're working on it. If you're working on a system, a lot of times you're probably working on it because something's not right with the system. So if that valve releases, one, where's your face? If they're outdoor units, those safety valves typically aren't piped
vertically up high. They might be right on the package at your head height, a little higher than your head. So where's my face, where's my body in relationship to that release valve? And then where's the back of my head? If I get startled and kick back, and I'm inside the rack, do I hit my head on the steelwork behind me? So again, safety valves, you need to know where they're pointed, where they go, what's behind them, and kind of understand how jumpy are if they release with them. Another item before I get into the PPE items you have to think about then is where's your body in relationship to when you're working on the components. It's kind of like the safety valves. Where's my head in relationship to the discharge of the safety valve? But where's my face? If I'm taking a valve apart or doing some work on it, taking a cap off a Schrader valve, do you want to have your face looking over the top of that in case that Schrader valve cap blows off? Probably not a good thing, right? You want to be standing back. Same thing for the center mass of your body, right? That's where your vital organs are. You know, you want to be thinking, if I can be working on higher pressure things, working to the side of my body versus right in the middle of my body is a better thing. You guys ever hear of the left-hand or right-hand rule? It comes for electricity, right? And that one isn't so much where's the shock going to go, it's which arm do you want to lose, right? So if you're turning on a panel for the first time, you don't want to be standing in front of the door. Because if there's a dead short, an arc flash in there, maybe the door comes off. Maybe the door swings open. So I'm going to stand, if the door has hinges on the left-hand side, I'm going to stand on the left-hand side and throw the switch. If it's hinges on the right-hand side, I'm going to stand on the right-hand side because you want to prevent, you don't want your body in where the main force is going to happen. So the same thing with CO2. You kind of don't want your body, your face, if something's going on, you know, trying to move to the side a little bit to work on it. So PPE, again, this is stuff you should have in your truck, things you bring along with you, things you ask the boss for. Safety glasses, again, it's cold. You could have cold, could be abrasive. You can have oil. You can actually have just plain old dirt falls off the machine room when you're doing something. So you want to protect yourself from that. Gloves are nice to have. Again, it's cold. And then, of course, on the discharge side, we tend to have higher discharge temperatures than other refrigerants. So you have the other side, and we don't talk about it a lot, but you can burn your hands, burn your arms hitting the discharge line, just like other refrigerants with that. So that's where you get into long sleeve shirts. Can be better. I know difficult. California is a hot area of the country, but again, personal protection for you. Safety shoes are nice to have. CO2 bottles are heavy. One falls over on your foot, probably crush your toes. If you have a safety shoe on, not so likely to have that happen. Then we talk a little bit about higher risk operations. So if you're charging the system, you've got more liquid available. You know, hopefully everything's connected right. Maybe sometimes it isn't. Maybe a line cracks or breaks on you. Start spraying some liquid CO2 out. Having additional safety equipment on would be a good thing to have. So that's where you get into the face shield. And to do training, one of the techs talked about it, pointed out that if you have a lot of cold material around your leather gloves, you can freeze the gloves to your hand. Well, that's a bad outcome, right? So he said, hey, you guys, if you're talking about you want to have higher risk PPE, you should have on the cryogenic gloves. So we added the little cryogenic gloves up there just as a thought. Not so dexterity isn't so good on them, but again, things to be thinking about that. So you want to, again, think about what you're doing, possibly a cryogenic apron. You want to really up your game and be prepared for that. But safety is for you. You're the one that goes home, you know, and hopefully you go home the same way you showed up in the morning with that. So with that, we're going to move along and start talking about the CO2 components themselves, just to make sure we all kind of have the same basic background on CO2 components. And maybe you've heard it once or twice, but 3 or 4 times hopefully drives it in that you really get a good feel for it, comfortable with it. So we hear the term transcritical only tells us one real thing about the system design, that it's going to go above 88 degrees and it will not condense. So that's the big thing. If I know it's a transcritical system, I know, okay, it's going to be hot outside. And in the United States, if you do air-cooled, you're transcritical sometime, all the time. There's no place in the United States you're not going to have at least one day, once in a while, that's going to get you that warm. So that's all. It's all it really tells you. Transcritical means above 88 degrees, and it means it's not going to be condensing at that point in time. Compressors, you could have a single stage compressor, one compressor. Compressors typically only operate down to about 0 degrees saturated suction. After that, the compressors don't have the capacity, structural capacity, discharge temperature to be able to function. So they're not out there, you can't get them. So something to keep in mind, if you get below 0 degrees, you're going to have a booster compressor with you. So if all you ever did was commercial work, grocery stores, they always want what? Ice cream cold? It's always going to be below 0 degrees when you're working with it. So you could come upon the thought that, well, transcritical systems always have booster compressors because every system you've ever worked on had a booster compressor. Well, that's only because you've always worked on systems that ice cream or whatever, something else with that. If you have a warmer application, if you go out and work on an ice rink's above 0, right? We don't need to be below 0 to make ice in an ice rink. You may only have a single stage compressor with that. So I made that mistake. Went to the ice rink they were installing, talked to our director of engineering, and I asked him, well, so where's the booster compressors? And he said, oh, there aren't any booster compressors, there's an ice rink. Oh, sorry, boss. So anyhow, avoid that thing is that really boosters only come into play when you get below 0 degrees. So transcritical doesn't mean where's my boosters with that. And a booster compressor takes the gas from the low temperature evaporators, pumps it up, raises its pressure, and raises it to the pressure of the suction of the high stage compressors. So it moves that gas. If you've done ammonia work, almost all the ammonia systems always have boosters because they're running relatively low enough pressure that they can save some energy and avoid high discharge temperatures with a booster. So they exist in the world of industrial for sure. Kind of new. I think there's some older R22 compound systems floating around out there that, I don't know, 20 years ago maybe, had some boosters in them as well. When you work with the evaporators, a transcritical system doesn't necessarily tell you what the evaporator is doing. You could have, with a transcritical system or a subcritical system, you could have direct expansion evaporators, using an electronic expansion valve, or you could have flooded, pumped over feed evaporators. So again, those evaporators are kind of separated from what's going up on the high side of the system. The evaporators look for liquid out of the receiver and do their thing. So what you're doing up here doesn't necessarily drive you to what's going to be going on the low side of the system. And then when you do transcritical systems, it may include some energy efficient components. Ejectors, we'll talk about that in a minute. We'll talk about parallel compressors to gain some energy efficiency with it. So after the compressors, we have the gas cooler condenser. And if you look at them, right, they look the same for the most part. If you were looking at them at a distance, you wouldn't know if that's a gas cooler or a condenser. You wouldn't know if it's from an HFC system or a CO2 system. So it's doing what we're used to with HFC systems. It's taking the heat of compression and it's putting out in the air, getting rid of that heat. So that's really what it's doing. But we do use the name gas cooler because when we're in transcritical mode, there's no condensation going on. If you had a sight glass on the outlet of that gas cooler and you're above 88 degrees, you won't see any liquid running on the bottom of the pipe. If it is, it's a little oil maybe, but no liquid refrigerant. You drop down below, gets below 88 degrees, you're looking at same sight glass, now I start seeing some liquid running. And now I'm condensing that gas. So that's where the proper name is gas cooler and then / condenser, because almost everywhere in the United States it gets below 88 degrees and you turn into a condenser. High pressure valve, so that's a new item, really not used in the unless you're doing some receiver winter pressure controls type of thing. You have a high pressure valve, and what it's going to do is it's going to drop the pressure from the gas cooler going into the receiver. Control on it is always going to go back. It's a back pressure regulating valve. Other people might use the term inlet pressure regulating valve. So it's going to regulate the pressure in the gas cooler. It's looking upstream. It's getting a control signal, open, close, stay the same, but it's trying to hit a target of what's in the gas cooler with that. Comes out of the gas cooler and we drop that pressure. So we go in, we've got a plasma. It's not liquid, it's not vapor necessarily. We drop the pressure on it. Poof, instantly we get a liquid and a vapor out of it. So that's what that valve is doing. It's there to keep the pressure up high enough, and then when I drop the pressure down, I get a liquid and a vapor. And then we go into our flash tank, and a flash tank operates really like a receiver and an accumulator. So the bottom half of the vessel is going to be receiver. I get that going through the valve, I've got a mix of gas and liquid. Drops into the receiver. The bottom of the receiver, we're going to fill it with liquid just like we do any other receiver. On the top side, we got all that gas. I got to process. I got to do something with it. Now it's acting a little bit more like an accumulator. I want the gas to come out of the tank, but I don't want the liquid to come with it. I want the liquid to stay in the bottom. I want the gas because compressors like dry gas. They don't want a lot of liquid. So when we do the sizing on it, first thing we look at how big a receiver do you need for the charge of the system, the size of the system. Then we confirm that the velocity is slow enough, the tank's big enough diameter that we're not going to suck out drops of liquid with it over to the compressor. Out of that system, then we have the flash gas bypass valve. So the flash gas bypass valve holds a pressure in that tank, and it's a back pressure regulating valve. Another term, inlet pressure regulating valve. It's going to keep that tank pressure higher. Because going where the gas goes from the flash tank, it goes over to the high stage compressor. If I don't have something in the middle to build up pressure in that receiver, I'm going to have a problem with my evaporator. If the receiver pressure, no valve, operates at the same pressure as the suction of the medium temp compressor, at the same pressure on the inlet of the expansion valve as I have on the outlet of the expansion valve, am I going to feed any liquid through the expansion valve? No feeding. So we need that valve there to generate a pressure differential to feed those expansion valves. So a lot of times we do sizing of valves. You're looking at, well, what do you size the expansion valve? What's the pressure drop going to be across it? We're looking at what do you think your receiver tank pressure is going to be compared to your evaporator. Usually it turns out 100, 125 pounds. But that's what it's doing. That valve is there to make sure there's a pressure differential to feed the evaporators in the system. Get it into a tank if you're doing a pump system or getting it through the expansion valves. So parallel compressor, remember I said that tank's running 100 pounds higher? If I can suck the gas out of that tank at 100 pounds higher with a compressor, it's going to be more efficient than the other compressor, than my normal high stage, right? Because whenever I go through a pressure regulating valve in a suction line, it does what? It drops the efficiency of the system. You don't want to have big pressure drops in your suction line. The system's efficiency drops. So if I have a 100-pound drop, that gas is losing a lot of efficiency. I put in a parallel compressor up here, I get a more efficient system. So that's what the parallel compressor is doing. It's processing the gas that's coming out of that high-pressure valve, coming out of that tank, and pushing it back up to the gas cooler. So it doesn't have to take a pressure drop and take a bigger step with it. And then there's some limitations. I mean, you can put a lot of parallel compressors in, so you have a lot of turn down. The reality is, from a cost standpoint, they get to a certain point where the parallel compressors are done. They're going to just shut off and cycle on and off. There's not enough gas to keep them up and running. When that happens, what the software does, it says, all right, we're getting to the point we don't want to be cycling our compressors. We're going to switch off, and we're just going to go back to the high-pressure expansion valve. So transcritical days, a lot of gas, tend to see your parallel compressors running. Gets colder outside, less gas, you tend to see those dropping offline. You're just going through the flash gas. And it's all about cost. You want more compressors, smaller compressors? Yeah, we'll keep putting them on, but that cost goes up a little bit. Typically for us, just missed that one. Let me show this. No. Yes. So we typically, I don't think we're unique in that, our lead compressors typically all have variable speed drives to try to trim the loads with that. And I think that's common somewhat in the industry. Then otherwise you'd have an ejector. So an ejector is a device that uses the pressure differential you have, because we're talking big high pressures at flow rate, to move refrigerant, sometimes a liquid, sometimes a gas, from a lower pressure point in the system to a higher pressure point, gaining some efficiency. Simple ejectors you may have seen in your life if you use a garden hose sprayer, right? Put on the end of your hose, got a tank on it, spray chemicals on the lawn, whatever. That's a type of ejector. Got high pressure water going through it, speeds up, low pressure, sucks the chemicals out of the tank. If you're more of a car guy, small engine guy, think carburetors, right? Got Venturi's down there, picks up the velocity, picks up, pressure drops down, we're sucking gas out of the bowl. So again, older cars, I'm an older person. Remember those good old days. So people have seen that, or you've seen those types of things. When you buy an ejector, it's a lot more sophisticated for a CO2 system than those real simple devices. Lastly, adiabatic gas condenser gas cooler. Everybody seen an adiabatic type thing? They're not just for CO2 systems. We have a couple customers. They look at the long-term efficiency gains on their HFC systems, and they buy an adiabatic cooler. Adiabatic coolers cost more, so they have a better benefit on CO2 systems. If they can help you stay out of transcritical, you get a better payback on your electric bill. So that's where you tend to see them more on the CO2 systems. What they do with that is they have pads. So they typically have some pads. They're, let's say it looks like a cross between cardboard and a paper towel. Doesn't look particularly impressive. You think, really, how long does it last? Years. Under the right conditions, they last years, right? Water conditions and ambient conditions. Dribble water down the side of those pads, keep them wet. Hot air comes in, cold air goes out. So it works really well in dry climates. If it's raining outside, is an adiabatic going to have the water running? No, because the air's as cold as it's going to get that day. So they can be efficient with that. And the advantage then, of course, is trying to stay out of transcritical mode. So you have all these days where maybe it'd be transcritical. There's an energy penalty when you hit that transcritical. You take that step, and it's a big step. Stay below it, you can save some energy. So state of California, I think code requires like half your climate zones can't just be air cooled. You have to have water cooled with that, or typically I'm going to wind up adiabatic. Okay. So some basic architecture. I'll get my little mouse guy here going here. So this is a really basic P&I piping and instrumentation diagram. And really it's only a piping diagram because I don't show any instrumentation on it. I just show the main components. And we'll see these a little later. They get a little more advanced, or get a lot advanced depending on your picture. But it's a way that you can show the point-to-point connections of the piping. Where does it start and where does it go to? It doesn't show you any elevations necessarily. You know, a lot of times the condenser's drawn on the top of the piece of paper because it kind of looks right there. But it isn't, there's no elevation. It's not showing you it's 20 feet up or 15 feet up or whatever else. It's really point-to-point connections on there. So we draw the components we talked about. You have a high-stage compressor, and I usually start with the compressors. On complex drawings, I can find them, and then I follow the lines around from there to hit the other components, see what's in the system. We go up to a gas cooler. Come out of our gas cooler, got our high-pressure expansion valve. So higher pressure at the gas cooler, lower pressure in the tank. This valve's going to maintain the pressure. It's getting a signal, so it controls the pressure in the gas cooler. Doesn't care really, for the most part, it doesn't care what's going on in the receiver. Flash gas valve really cares about what's going on in the receiver. It's looking back and it's getting a control to maintain that. And as I said, all right, if I don't have that valve, that gas would go right back to that compressor. If that tank was the same pressure as a compressor, no flow through the evaporator. So that gas can go back through there. And then coming out of the tank, we're going to have liquid. The liquid's going to be just like any refrigeration system. It's going to feed an expansion valve. The expansion valve is going to go through the evaporators. Medium temp, it's going to go in up to the high stage. Low temp, it's going to go over to the booster. When it comes to the expansion valves and the controllers aren't really unique when it comes to CO2 refrigerant. Mostly you're taking the controller and you're picking your CO2 as a refrigerant instead of some other refrigerant. Valves, the same thing. Most of those valves are going to size them appropriately. Right? They have to write pressure rating, that type of thing, sized appropriately for it. But that aspect of it, if you're used to doing electronic expansion valves, CO2 are just electronic expansion valves, not a lot necessarily going on with that. Danfoss has a mechanical valve out, although I didn't see it at the last show, so they're somewhere in the process of putting out some mechanical valves. So someday in the future, you may not say that all CO2 valves have to be electronic. Maybe a one. Right now, If you bought any equipment, it'll be an electronic valve on that. So with that, what you can do with that system and what engineers do with the system is they can lay it out on a pressure enthalpy diagram. So they can take the information, take the components on there, and the pressure enthalpy diagram has pressure on the side, low pressure at the bottom, high pressure on the top, and across the bottom it has energy or enthalpy. And the slide deck will be available through the NASRC, and the numbers correspond to it. So you got number 1's a compressor, and you can see how it's drawn over here. It picks up some energy and also picks up some pressure. So we'll look at that in a little more detail in a bit. Pretty simple diagram. This is from Emerson. They made available. We have one of these on our wall in our lab. It's a nice layout from them because you have some of the color coding, right? So as you look at the componentry up here, again, you've got numbers on it, but you can go down on the bottom and see some color coding that goes with it. Nicely labeled, tells you what the evaporators are, that type of thing. Other thing you have with that, they included the pressure temperature chart with that. Normally, I see there's a Sporlan one laying here. Used to carry Sporlan around. Now it's on your phone as an app, right? You look up the refrigerant, what's the temperature pressure relationship. But something to keep in mind, notice the chart ends 87.8, about that 88 degrees. You get above that point, you're in transcritical mode. There is no temperature pressure relationship anymore. That doesn't exist. So now when I'm down lower here, if I have liquid in a pipe and I can measure the temperature of the liquid in a pipe, I know what the pressure will be when I put a gauge on it. It matches across this. Get above that, measure the temperature. The only way you want to know what that pressure is, you have to put a gauge on it. You can't predict it, can't look it up on the chart. Same thing when you go down at the other end, you get below the 60 psi mark, you wind up in a dry ice mode. So now it's dry ice, there's no temperature pressure relationship anymore for that refrigerant. And again, like I say, we always talk about you don't want to get below 100 pounds where you might start forming dry ice with that. So looking ahead here, next one, blow up the pressure enthalpy diagram. So what you can look at there is pressure. Pressure's on the left-hand side of the screen, and it's a logarithmic scale. So logarithmic scale kind of compresses it so it fits on a piece of paper, right? Seems simple, but it simply does that. Fits on a piece of paper. If you didn't have a logarithmic scale, you'd need a really tall piece of paper, and these diagrams are available for all refrigerants. They all kind of look alike. They have this dome in the middle. They have the lines. They're all very similar. Not identical. Properties change it, but very similar to that. So the pressure is going up on the left-hand side. Across the bottom then is the enthalpy. Enthalpy is kind of a fancy term for energy. So I start on the left-hand side when it represents what's happening in the system. As I move from the left to the right, I'm gaining energy. So an evaporator is when it's drawn on here to represent an evaporator, I start out at the evaporator on the left-hand side. Got a lot of liquid in there. It's absorbing energy, right? It's cooling the air. The refrigerant's warming up or gaining energy. As it gains energy, it's shown going across to the right-hand side. So it has energy on it. You have the opposite for a condenser. I start out over here. It's got a lot of energy. It's hot. As I run it through the condenser, or in this case the gas cooler, I'm going to cool that down. The energy drops. I now have less energy in it. So I can reuse that refrigerant, start out with low energy, heat it up in an evaporator, and move it around. The other item that, we're going to look at temperature is pretty important. These curved lines, as they sweep through, they represent a constant temperature. So if it's 100 degrees, and we'll see it on another one, there's a line that represents 100 degrees. So if your system is operating at 100 degrees and you wanted to draw it on here and say where's that point exist, you'd wind up following the 100-degree line. Then you'd look at what's the pressure gauge, you put that point in there. Other thing the diagram talks about or gives you information about liquid. So it tells you when I'm over here on the left side of the dome, it's all liquid. When I'm over here on the right side of the dome, it's all gas. Notice our compressors are over here on the right side of the dome because they like gas, right? They don't want to have liquid. In between, it shows you the mixture, and it's an accurate representation of the percent of the liquid in the system and the percent of the vapor. So if you took a chunk of it out and measured it, if you're right down the middle, by weight, half of it would be liquid and half of it would be vapor. If I start out over here and I measured it, I'm going to have more liquid by weight than I am by vapor. If I'm on the right-hand side, I'm going to have more vapor than liquid. And it's pretty important because we're going to, as we look at the representation, we're going to want to know what that percentage is. It explains why a gas valve does what it does, why the software is making that change. So evaporators, it's kind of a point-to-point as you build these. If I was going to build this from scratch, I'd look at, the customer's going to tell me how cold he wants his stuff, right? You want ice cream, minus 20, a good evaporator. Okay, I'm going to draw a line. I would draw a line for minus 20. He'd tell me what his medium temperature load is, right? You're always going to know that. I want to have a 20-degree evaporator to keep the meat cold or whatever he's doing with it. I would draw a line at 20 degrees at a constant pressure. The next thing I'd know is I'd look up what the temperature is for the ambient, right? If I'm going to have a outdoor condenser, what are my design temperatures for those days? If it's going to be, say it's 90 degrees, I'm going to be 100, and you'll see that in a moment. I'll highlight that line, and I know somewhere when I come out of that gas cooler, I'm going to be at 100. I'm going to be on that line because it's going to be 100 degrees coming out of that cooler. And when you put these together, you wind up kind of just connecting dots on them. You come out of the evaporator and you go, all right, I got some superheat. This line tells you the temperature. You can drop your point for 11. You look at the software, it tells you what the discharge temperature is going to be. I can find that discharge temperature line. I drop a point. Suction to discharge, I draw a line. Same thing when I move back into the, that discharge gas is going to go back to the compressor. It's going to get cooled off somehow, moves to the left. And how much cooling it is will decide where you put that point. And so you can go through and drop those points. Main thing we want to stay focused on is that the condenser is going to be a horizontal line. We're assuming no pressure drop. And when we go through an expansion device, it comes out of the condenser and it doesn't change energy anymore. All that energy exchange happened in the condenser or the gas cooler. It's just strictly a pressure change. When I drop down, that pressure change, where it hits my line, which is the flash tank, when I get to 0.4, that tells me how much gas I have and how much liquid and how much vapor I have. So we're going to be watching, where does that point move? Is a point moving to the left as the system conditions, operating conditions change, or is the point going to move to the right? And if you're doing flash gas, does it have any value, any refrigerating value in the system? Not really. It just goes around and around. You recompress it, you cool it, you recompress it and cool it. Which is why transcritical CO2 systems aren't so efficient, because you're kind of running this gas around the loop and not doing much of it. So if you want to get the most efficiency out of your system, you would always strive to have as much liquid as possible. You don't want to have gas. You don't want to have gas coming out of it. So we're going to talk a little more now, a little more detail. That was just the opening salvo on the pressure enthalpy diagram. We're going to talk about using a pressure enthalpy diagram. We'll talk about then the optimal operating point. What is the software picking and kind of why is it picking that point? And then it's going to be kind of a looking at flash gas minimization. Then we're going to compare some system efficiencies. I'd used the Bitzer software, ran some different discharge pressures for the same temperature, and we can see how that works. Then we'll tie that back to why do we have the operating point that the software selected on it. So back to the pH diagram, and the guy that made this is just, they've been around forever, but really clever. All these, you see all these different values on there, all used for different things. And as a refrigeration engineer, very, very useful. But what we're really going to be concerned with as it relates to the high pressure valve, we're going to be concerned, like I said, mostly liquid on the left-hand side, mostly vapor on the right-hand side. When we follow our temperature lines, where is that going to drop in? Am I going to drop in on the liquid? Am I going to drop in more over by the vapor side with them? So, and this is Corel. We have a Corel individual in the room with us here. So this is out of their literature, and I think that actually tells you, if you want to go find their literature, that's the file on it. But it indicates what their software is going to be doing to operate at the optimum point, give you the best coefficient of performance of your system, right? Give you the most cooling for the energy you're putting into it. When you're down in subcritical mode, that's a punched in number. Usually you're looking at having a minimal amount of subcooling, and that's a number you punch in. The software is not deciding that for you. If you want 3, 4, 5 degrees, typically is the number. And to get that subcooling, we're condensing, right? So we're getting liquid out of the condenser. To get that subcooling, it's going to close off that valve and back a little liquid up into the condenser. So it's going, when you back liquid up in the condenser, you might raise the pressure in the gas cooler as well. So that's all going to happen. That's going to kind of just move up, and it's going to control that. You have a transition point. I think a lot of times they'll say the transition point, decide where it wants to stop trying to be subcritical and where it wants to be transcritical, and they just set a target for its control. When you get up above the transcritical point, now it's looking at an optimal pressure based on the leaving temperature of the gas cooler. And there's a formula that's been derived, theoretically tells you what is that optimum pressure based on your leaving temperature. And it's pretty much the same formula for everybody, right? Some of the guys may have tweaked it a little bit, but the compressor guys are pretty much using the same formula. All the control people are using the same formula. So that line, when you look at different people's literature, is going to look pretty similar. What you notice on the line, though, it kind of goes around. See how the curve comes around and all of a sudden it breaks and start going up pretty vertically? That line tends to drop right through that inflection point there a little bit. And what you're looking to do, what the software is doing behind the scenes and through that formula, is it's trying to balance getting more liquid. And we're going to see in a moment on the next slide, to get more liquid, I have to raise the pressure. If I raise the pressure on a compressor, what happens to the energy? Go up or go down when I raise the discharge pressure? Goes up, right? I'm going to be paying the electric company more on it. What happens to the volumetric efficiency of the compressor?
Goes down.
Goes down, right? So it's kind of a double hit. So when I raise up the pressure, it's costing me something. On this side of the balance beam, it's costing me something. It's costing me more energy, some losses in capacity. On the other side, I'm going to get a lot more cooling effect out of the refrigerant I am circulating. So that's a win. So that software is taking a look at it, and it's making a decision and saying, for the leaving temperature out of the gas cooler, this is the optimum operating pressure for your system to get the most efficiency out of it. So I mentioned a couple of times now the leaving temperature of the gas cooler, right? We're looking at that. So it turns out of all the different sensors you have on a system, that's probably one of the most important ones that you really want to make sure is well attached, well insulated on it. Because you think about what's going on, that sensor is probably going to be controlling your fans. It's going to look at what's the leaving temperature and what's my air temperature. Should I turn the fans up a little bit, get those two temperatures closer together? Should I turn them down and wasting energy? So you're going to be looking at fans with that temperature. The other thing is the software is going to be constantly looking at that temperature, making a control decision. So controls like to have good information so they're not real twitching on it and not working well. So you want to have that on there. You want to have it tightly attached. So typically you're looking at a mechanical clamp. You're not duct taping it on there. You're not putting a plastic wire tie on there. You might be getting a copper strap that you'd use for an expansion valve bulb, putting that on there, getting the, I guess I call them radiator clamps, the stainless steel screw down clamps. You want to get it on there. You may want to put some heat transfer paste on it. Definitely want to insulate it, right? So you got those probes, you know, they're 2 inches long. You don't put 4 inches of insulation on it. You know, a lot of insulation. You want to get them close to the condenser, and you want to be on the common line. If you've got 2 circuits, you want to be on the common line after that split. And you want to insulate upstream, and you want to insulate downstream because it's controlling, and that drives it. Because you think of other things, you've got compressors. I said I got VFDs. They're running on PIDs. And I've got all the expansion valves. They're running on PIDs. My flash gas valve is running on a PID. You got all these things running around on there. If they get good information, the software has a better chance of giving you good results. So that's just a, you know, if you're having trouble with the system, you're having sort of not a lot of control, you might want to take a trip to the roof to see how that baby's hanging up there. If that high pressure valve's not moving around much. But anyhow, so this is a simplified version. I only showed the top half. So I drew in a heavy black line, 100 degrees. And I said, all right, it's 90 degrees outside. I'm only going to get this cooled to 100. So no matter what I do with my high pressure expansion valve, if I open the valve and drop the pressure, right, open valve lets more of it flow through. If I close the valve and hold the pressure back at a higher pressure, nothing, you know, this is a simplistic world, nothing's going to change. That temperature's still going to be 100 degrees. So no matter what I do with the valve control, with the pressure, I'm going to be riding along that line. That's the point I'm going to start with. When I come down, I'm going to connect down, vertically down, because it's only a pressure change, and I'm going to hit my flash tank. If I raise my pressure up to the left, software says I want to go up, I'm going to move up to the left, going to pay a penalty, more electricity is being used, a little less efficiency in the compressor, but I'm going to wind up getting more liquid. I get less flash gas, I get more liquid, possibly better efficiency, possibly more capacity. If I go the other direction, I lower that pressure. I wind up getting, now I'm dropping in down here, and I didn't necessarily have to lower the pressure a whole lot. I'm getting a lot of flash gas. I'm not getting a lot of liquid. Losing capacity in the system, losing efficiency in the system. So we're going to, as we look at these simulations from the Bitzer software, we're going to look at where is that line dropping in and how does that line shift to the right or to the left as we change the pressure in the system. So I went in and I guess you can see that, went in and selected some compressors, locked them in so the compressors didn't change, let the software go back and calculate the system pressure that it should run at, and it came back and it said 1351. Odds are if you went into a controller and it was running, it'd come back and say it'd run 1351. The only thing you have to watch out with the software, PSIA came out in absolute units versus gauge, right? So if you're looking at it, you can say, well, it's 15, you know, if you're, it's had nothing to do better in your life, and you keep looking at the Bitzer software, keep looking at the controller software and wonder why it's always 15 pounds off. One's maybe in PSI and one's in PSIG. So you see that the calculations, a lot of times with CO2, you'll be in absolute units with PSIA. If you want to have PSIA converted to gauge, you add 14.7. Right? You think about that, your gauge to absolute, you add 14.7. So gauges always read 0, but we actually know that air is pressing down on us, so we add 14.7 to that. So anyhow, it gives you the capacity of the system, and what you want to really look at, we're going to watch how it moves on the next slides, is this vertical position. What do you guys think about how much gas do you think we have versus liquid there? 65. Yeah, 65, 35. We got more liquid, right? We're definitely past the 50% mark, so we're over there on the liquid, and we're letting the software, everybody knows, you know, it's not a secret to calculate the best position. So our controller will be trying to maintain 1351 PSI as well. I, however, know better because always when I've run into capacity issues on HFC systems, I always knew it was important to lower the head pressure, right? You gotta, you know, things are warming up, it's a hot day, let's get that head pressure down and we will do more cooling. So I assume the person that put the controller together and did all that programming. It was dead wrong. Got it wrong. Somebody checked an invert box someplace in the software. So I'm out there and I know a lot more about it. I force that valve open to drop its head pressure because that's what I've learned my whole life. And I dropped the pressure down to 1200 psi. Everything's great. What do I have now? Do I have more flash gas or do I have less flash gas? So what do you think is going to happen to the cooling effect of that system?
Down.
It's going to go down. We'll see in these tables when we get to the end, we'll have those together so we can see how dramatic that is. And how bad it would be if you thought, boy, let's drop the head like we've always done, lower that pressure and think I'm going to do better, and then you're wondering why the suction pressures keep going up. So if you did that and noticed things got bad and said, well, I can always reverse, you know, go one way, turns out bad, turn around and try the other way. I'm going to raise up my pressure. I'm going to go up to 1500 psi. Keep in mind, I'm still stuck, right? Still stuck on that 100-degree line because it didn't change. The temperature outside didn't change. Now do I have more or less flash gas? It's a little tricky. We'll go back. Get a little less flash gas. It's moved over subtly to the left. But I'll give you the tables here momentarily. So this is the table that was on the bottom of those graphs, right? Hard to read table, blew it up a little bit so you can see it. So the first column is the target, 1351. Next one over is when I thought I knew better, I was going to drop it to 1200. And then I said that wasn't working so good, so I went back up to 1500. COP, coefficient of performance for the whole system. And you can see bigger number is a better number, more efficient. So when I went to 1200 psi, I kind of took a hit. And some of these numbers, when you look at them, they don't have a big number change by itself. You think, well, okay, it went from around 3 to 4 3/4. What's 1 1/4? When you look at the percent change, it's like, it's over a 33% change. So again, when you deal with small numbers, it's the percent difference that changed, not the absolute value. Change by a degree. Well, how much cooling you're doing? Well, we're only trying to cool at 5 degrees and I'm off by a degree. That's a 20% difference. So you got to be aware of that when you look at these. Small numbers can be significant on the electric bill. When I went to the higher one, 1500 psi, COP is still not as good, right? Software says, no, you should have stayed at that 1351. So the rest of these items relate to the low temperature side of the system. You see any differences?
Yeah.
Where do you see a difference?
Your COP.
Nothing.
Just COP is the only thing that's changed.
Right, and that's for the whole system. Because really when you think about it, those pressure the pressure enthalpy diagrams, that low side's kind of all by itself down there. Those systems, it's getting liquid out of the flash tank. The flash tank pressure doesn't change, the temperature doesn't change, that compressor just keeps chugging along. Nothing's changed for it. That discharge pressure hasn't moved. Compressor's sort of isolated, maybe is too strong of a word, but that's sort of what it is. It's sort of separated out of the system. High side of the system, whole different ball game here. So notice some of the numbers changing, right? We got the same values, pressure and COP at the top, but look at the evaporator capacity. So when you go down at 1200, you'll know why they keep complaining about warmer food. You're going to have some problems there. Now this is a simulation, so the reality is what's going to happen if you're in a store, you're going to see what with the suction pressure? Up, 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 up. You're going to keep wondering why I can't maintain my suction pressure on my high stage compressors. You're going to be generating flash gas, they're still ripping along flat out, and the pressure just keeps going up. The lower you make the head pressure, the higher the suction pressure goes up. So that's what you'd see because, the evaporator doesn't know to, let's stop doing so much cooling and let the flash gas do it all the work. You're just going to have more gas and it means higher suction pressures, and you'll lose capacity that way. So the evaporator mass flow then follows that. Evaporator capacity kind of takes a chunk with that. Gas cooler goes up a little bit, right? Lower pressure, I get a little more efficiency out of my compressors, can pump a little more Gas through the compressor, I have a little bit higher mass flow in here. Same thing happens, I get up to 1500, I'm going in the other direction, not quite as much mass flow through that. Power moves around as we expect. Lower discharge pressures, lower power consumption, higher discharge pressures, higher power consumption. And then of course current goes around with that. Mass flow is kind of the same thing with, I'm trying to think which gas flow that is. Flash gas mass flow, again, this is where you see that huge number pick up, right? When I started dropping down on that line, I start moving to the right really quick, I get a lot of flash gas. So you have a lot of flash gas being generated with that. Superheat drops down a little bit. Reason superheat drops down is as you generate more of that flash gas, it's actually cold flash gas. It'll actually be a little bit wet, a little bit damp. So as I put more of that load into my system, that's going to make the overall suction colder. Discharge temperature, notice what's happening there. A lot what we expect, right? Higher the discharge pressure, the higher the discharge temperature. This system, the software may be starting to say you're done at 1500 psi because I'm getting up to 279, right? That second override's going to come in and kick that back. The one thing, and let me just scan back, do want to touch base on the system here. When you're doing troubleshooting on a system, this is just sort of an true, but maybe you don't think about it. Those compressors, if you have medium temp evaporators, that high stage is going to have 3 different gas flows. So you're going to have gas flowing out of your gas cooler, you're going to have gas coming out of the evaporator, and you're going to have gas coming up from the discharge of the compressor. So if you're working on superheat, I got too much superheat, I got too little superheat on that compressor, you need to think about what's going on those 3 different mass flows, right? So that's why that temperature dropped, because this is really cold compared to the other 2. As I put more really cold gas into that mixed stream, it pulls down the suction temperature of that compressor. So something to be aware of. We had a customer remoting into the store and they were having some low superheat alarms on the compressor. So we spent a lot of time, they had a lot of evaporators, looking at the superheat on the evaporators. Eventually ruled those out and found out that we were getting low temperatures. Actually, the low superheat was coming from the flash tank. Sent somebody in the store. They had filled up the system above the top sight glass with refrigerant. So they were vacuuming liquid refrigerant out of that receiver. So got them to drop it down to the center sight glass. All is well. So just something to be aware of. You got this extra stream that we're not used to seeing. We're not used to seeing that. Besides, the booster is going to be hot, so we're not used to seeing that. So some things you have to be aware of when you work on it. So that's kind of the story with it. That's why the valve does what it does. It's trying to mitigate that flash gas. And the higher the pressure, the more liquid you get. The lower the pressure, the more flash gas you're going to get with that. And things would change if you raise this up, raise the pressure up on that. Your discharge temperature is not going to be 100. It's going to go up above 100. So in a real system, there everything's moving around, right? I'm on paper here. It's not happening. You don't see all those interactions going on. A lot of the software out there does allow you to pick if you want to switch from optimal efficiency to maximum capacity. A lot of times they'll have a capability, they can let you switch that, flag that down. So if it's a hot day and you're like, I don't care what the electric company says, they're complaining about the temperature, it'll switch over and start pushing that pressure up. Still has other safeties, right? Discharge pressure, discharge temperature, but it'll start moving that up.
But that would bring our superheat up as well, correct?
Yes, because you're gonna have less flash gas going into that item. And we're not, you have different sessions, it's, desuperheaters, liquid to suction heat exchangers, injections. So there's a lot of other stuff that goes on. We're kind of just pretending like we don't know and it all works well. So high pressure safety. So some of the systems, depends on the system, will have things to help avoid getting a high pressure in a segment of your piping, possibly a vessel, whatever. And one of the ways is a back check valve. So if I closed off sections of my piping, it's isolated, did it inadvertently, and the pressure starts building up on there, in a lot of cases there'll be a check valve around that isolation valve. So that check valve will open up, it'll bleed the pressure down. So if I'm isolated, this pressure starts going up, it bleeds it into that line. And we'll see on some of the drawings, then if there's another isolation valve, there's another check valve. A lot of times that bleeds back, you follow the trail back to the receiver. Is where you go with that. So that's out there. Otherwise, there's another brand of valves out there. It has an integral check valve built into it. So there's not a valve, you won't see something piped around the outside of it, it's all built into the body. It's the same premise. If I close the valve and the pressure builds up here, instead of rupturing the pipe, it bleeds that through the valve body itself and lets the pressure go down. So those are two items that can be used to help maintain or prevent an overpressurization in the system. Another item that can be used with that and by code is required in a lot of application is a regulating relief valve. So with relief valves, you get above a 6-inch diameter vessel, you're supposed to put a relief valve on it by code. And when you put the relief valve on it, that relief valve is designed that in case of a fire, it's going to let the gas out of the tank so the tank doesn't explode, right? Fire, tanks exploding, people die. So that refrigeration system's been around. All your systems have those relief valves. It's not CO2 is the only one. If you have a fire, tanks explode, people die. So been around for everybody knows to put on relief valves. Those are all sized for fire. So they'll let a lot of gas out when they open. That's what they're designed to do. They're designed to drop that pressure down in the event of a fire. Well, if your pressure's going up because you lost power, it's not a fire, it's kind of creeping up a little bit at a time. Then what you wind up, you say, well, I don't want to have it all of a sudden blow that relief valve down and lose a third of the pressure in the system. I'm going to put on a physically smaller relief valve that's going to burp and let out a little of the CO2 pressure at a time. It might continue to burp, right? Power's still out, pressure comes up, it burps them out. Power's out, burps them out. So you'll put in a second set. So that's what you have here, called a regulating relief. Notice the set pressure is less than the main pressure in the system. So this guy's going to release first. You're going to keep burping, burping, burping. Hopefully you never release the mains on there unless you'd have a fire with that. All of these have relatively low pressure closing forces, right? Your check valves may be magnetic, may be lightly spring loaded. So there's not a lot of closing force. The safety valves, when you're up near this design pressure, there's not a lot of closing force on it. So when things go through refrigerant lines, right, you got oil and refrigerant, what else does it usually carry along with it? Dirt, right? So if you have dirt going through your check valves and your whether it's a side check valve, a ball check valve, or you have dirt going through your safety relief valves, you have a chance they're not going to seal down tightly. So that can create it creates a service challenge, because if you worked on a section, you isolated it, now you want to pull a vacuum on it, but you got something underneath that check valve, you may not be able to pull that vacuum on that section, right? So you hook up your vacuum pump, you try to get as low a vacuum as you have, maybe get it down below zero, whatever. You may be in the flushing mode, right? You may be able to try to isolate another segment upstream, but sometimes if you're going all the way back to the receiver, you're not going to blow the receiver down because you can't pull a deep vacuum on the suction, or on the filter dryer, right? So that's where you're going to be pulling down a vacuum, maybe flush it with some CO2, pull it down, flush it with some CO2, but you're not going to be able to get a deep vacuum like you would like. So that's somewhat of a challenge with that. On the safety valve standpoint, if you have one leaking, you need to change it out then. And I don't know if you're all familiar with the three-way valves on there. The three-way valves are designed that you're either on one port or the other port. Some of the valves, I think you can't be in a middle position, but you do not want to operate those in the middle position. We had a customer, he was ordering 2 safety valves because he had a release, and we asked him, well, what do you need 2 safety valves for? I had a release, they both went off. And we're like, okay, not really. That valve should have been isolating one side or the other. So and it's the same for all the valves and all the systems you have today. But odds are, because usually an HFC system never releases, you never would have noticed that. You never would have had experience knowing you need to be on one side or the other. Because what you want to be on there, you want to be on one side. Let's say I've closed off the left-hand side, I'm on the right-hand side. The safety valve releases, get some dirt underneath, it's leaking. I can come back, I can switch the valve over, close off the right-hand side. Left-hand side is doing protection. Right-hand side, isolated from the system, can be removed and replaced. So when you have the three-way valves, it's one or the other. Don't leave it in a midpoint position. That way it gives you a chance to service it if you need to down the road. So another technique used to improve serviceability in the system, they'll have two different pressure relief valves on the same system. So it's not these are both fire rated valves, so it's not a regulating relief. What it is for service related. So the liquid line going out to the system is rated at 650 psi. During normal operation, I want that three-way valve open so that 650 psi is protecting those lines. If I'm doing a service activity, I know the system's going to be down, there's some maintenance project we're doing, repiping, power company said we got to shut you down for whatever. You know it's going to be down for maintenance. I can pump down those liquid lines back into the receiver and I can switch over to a higher pressure safety valve. The reason is that receiver was designed for a higher pressure. And receivers, higher pressure means thicker walls. So that's why everybody doesn't just buy really high pressure receivers, because they get really expensive and they get like thick walls with it. So anyhow, that's a technique to allow more serviceability, less likely to have a release refrigerant and have to add more back in. You switch back and forth. When using that, important that you need to switch back to the 650 when you're done with your maintenance activity. Because again, you're not maintaining up at the safety valves, you're doing your work over here in a different part of the facility. You need to remember to go back and get to that safety relief valve. And in one tech we were talking about, he said what he would do is he would put his car keys, truck keys, on that safety relief valve. Because he knows he's not going to forget his truck keys because he's not going anywhere. So that's just as a reminder that, hey, I got to go back and do it. Or you tag it something, put a thing in your phone, whatever. But it's kind of important that you wind up putting the system back to what it needs to be. So with that, that leads us back to, or leads us to the next topic, administrative controlled component isolation. That's 4 big words. What it means is technicians need to be with their A game when they're servicing equipment. You need to be thinking, when I'm isolating segments for work, am I isolating liquid refrigerant? Am I isolating liquid and vapor refrigerant in there? And if I am, how am I going to drop the pressure down to a safe level? So this is a picture, we'll see the full drawing here. There's a big system, they had three liquid filter dryers on there. So you could isolate one of them, change it out, put it back in service, change the next one out. So with the system, if I close both of those valves, the liquid filter dryer is going to be what? Full of liquid. So that would put me at a high risk, things start warming up with it. So you have to really pay attention, you don't get distracted and walk away. You know, sometimes you start hearing some noise, sounds like the compressor's crashing at the other end on you. You get a phone call, it's important. You don't just walk away, you got to open one of those valves back up again. Release it back into the system. Same thing comes into play if you're going to do the service work and you're like, well, I'm going to bleed off that pressure and I'm going to use a gauge set to do that. Well, come in with your gauge set. You don't isolate the dryer, then go find your tools and your gauges. All right? Maybe you get distracted again. Now I'm building pressure up there. It can be a problem with it. So it comes to paying attention to what you're doing from a safety aspect, from a service and isolation standpoint. So administrative controls have the advantage, they don't have all those little check valves flopping around in them. They don't have a safety relief valve. Without the check valve and without the safety relief valve, when it comes to servicing, it's a little easier, more what I'm used to with that. So you tend to see that more in industrial applications will look for that. They have more confidence they have the same group running it, it's in their own facility, their own maintenance crew on it. You will not see administrative controls used with automatic valves. If you have an automatic valve, you will have one of those other automated safeties on there. So let's say you had a solenoid valve and you had EEV valves. Solenoid can shut off, EEVs can shut off, you would see a check valve then, right? From our company, you'd have a check valve, because those can happen automatically. You're not having a technician go out there and close them. It happens. That's what the software is supposed to do. It shuts it off. We don't want to trap that liquid and have it move with that. So those will be in there, but it is paying attention to what you're working on. So with that, let's take a look. Oh, we got one more to talk about. Compressor safety valves. So again, this is just something to be aware of. We use different brand compressors. These are all kind of popular in the States here. And they almost all of them have safety valves on them. Depends on what the code requires with it. And you need to be aware they're not all the same. So it comes back to, again, knowing your system when you start working on it. Bitzer safety valves on the low pressure compressors, their safety valves are isolatable. If you back out the valve they're on all the way, it'll backseat that valve, and that safety valve is not protecting that compressor at that time. As a result of that, we and other manufacturers put a safety relief valve in the suction line. So if you back the valve out all the way and the pressure goes up, that safety valve will release. Turns out compressors are probably generally your lowest designed pressure design component in the system. You know, they'll be 350, I'm sorry, not 350, 435, 500. The rest of the system's 650. Compressors on the boosters tend to be the lowest pressure design system. So you could easily get above Bitzer 435, so that's why that safety valve's there to prevent that. So it's one of those things you don't want to go, well, I had a problem in startup, I released, the safety valve was leaking. Doesn't look really important to me, so I put a plug in it. Not so good for the compressor, cast iron compressor. So anyhow, you got to be aware of that. There'll be discharge valves, so again, you want to look at your compressors before you start isolating them. Where are the safety valves, because they are different on the different components. Other thing to be aware of with that, a lot of the systems we have out there, I've seen that with competitor systems as well. The safety valves, when you look at them, they do not have an NPT thread on them, the valves used by the compressor folks. So typically they are not piped to the outside. They usually have deflectors on them built right into the valve, so if that valve would release, it won't spray at you, it'll spray at the compressor, then it'll fan out over it. So something to be aware of, where your body is in position and what you're working on, right? That valve's there, should you have some oddity, and it's got to be pretty odd to have the high pressure safety release on a compressor. You got a high pressure cutout. Software is going to try to turn it off, so, but just something to be aware of that. These are different, just lay out the differences with it because it's something to know. So this is a piping and isometric diagram, system we provided to a customer. This is somewhat of an industrial customer. Zero Zone calls them M1s. I'm not sure what the rest of the people call them, other than generic name is piping and instrumentation diagram, P and ID. I've heard somebody once call them PIDs. Well, that's kind of confusing with control, right? Controls have PIDs. These are piping and instrumentation diagrams. So it gives you, again, the information that's on it, what you can follow it, find something you like, and start following the lines out of it, follow the arrows around on it. This one is the example where we have the regulating relief and the main relief up here showing up on the receiver there. This system turned out they wanted, industrial system, they wanted to be able to just turn it off if they didn't have a cooling load on it. So we designed it at 90 bar. All the components in the system are 90 bar. 90 bar is above that transcritical point. So this system you just shut off, walk away. Having trouble with startup, shut off, walk away. You're done for the week, shut off and walk away. Nowhere in the system will, really, unless there's a fire in the building, will you ever get a high enough pressure to cause a relief valve to go. It doesn't happen. So we do that. More industrial customers, not so available on the commercial side. Our display cases, 650, 700 pound coil design, not really 90 bar coils type of thing, doesn't exist. So you get it more in the industrial application where you can buy a little higher pressure evaporators with that. This guy here, interesting, we talk about serviceability. If you notice, if I wanted to change the suction filter, right? That sounds like something we might wanna do a couple days after startup, whatever. I'm gonna need to isolate it. We don't show up, but these compressors actually do have isolation valves on them. There's an earlier drawing. We're gonna isolate at the compressors, that sounds good. And I'm gonna go over here and I'm going to isolate on my suction lines, right? You notice that little oddity on there?
Not really.
A little bit hard to see. The other room had a better display. On that little oddity, that's an indication of one of those ball check valves. So it's a check valve built into that ball valve. And it's checking in this direction. So if the pressure downstream of the valve drops, it's gonna let something in from upstream of the valve. So if I close those valves and think I'm ready to service, and I start trying to bleed the pressure out of there, I'm gonna be surprised because I never get to bleed the pressure out of there. It just goes on and goes on and goes on, and it's not because the valves are broken, it's because that valve was set up as a ball check. It's supposed to let the gas through in that direction. So if I wanted to service that, I need to pump down my lows, I need to pump down the whole low side. I'm over here, I'm closing ball valves on the liquid side as well. Not a real service-friendly application. So that's what you run into when you have the ball checks and things like that, that sometimes it's just not real service-friendly. You know, you gotta do more things. Yes, sir?
So the check valves of those valves are actually just looking at differential. They're not looking for a specific pressure to open up.
Yeah, they're just spring, you know, you think of it like a spring-loaded, right? If the pressure gets high on the other side, opens up, or a magnetic check, whatever the half pound on the magnet is, they will just open.
Okay.
So they're not a, you may find some valves, depending what different companies are doing, that would be like an inlet pressure regulating valve, and they're gonna let the pressure out. So we typically haven't done that, but that's not to say others in the industry don't. So that's one of the reasons you wanna. Is it? Oh, that's the reason you wanna get these piping and instrumentation diagrams. And you know, if you're on a job site, you call up the factory to email you the PDF of it. And I think all of our competitors would as well. Our drawings, when you look at them, and we're not spending a lot of time on it, they don't look alike. We change stuff. It depends on the load, the customer, what they want to have happen. Energy saving techniques that are going on, safety related issues. It changes a lot. And that's just us. That's not the other guys doing whatever they do differently. And we don't know what they do because they don't mail us their drawings, imagine that. So if you're a technician working on it, you really want to be saying we should get the drawing, and when we get it, we should post it so the next guy coming onto that job can look at the drawing and see what the valves are and what's going on. That's just going to be really good maintenance practice. This isn't like HFCs where all the, you know, after a while HFC systems all kind of got to be the same, right? You'd show up, you kind of know what's going on. Not so easily here. A lot of different things going on. When you go into troubleshooting, okay, that one's got a heat exchanger on, there's something wrong with the heat exchanger, is it cracked, is it bleeding? The diagrams help you see all that without trying to follow this maze of black snakes. Very difficult. This guy here, again, where you look for safety valves, we have safety valve protection. The safety valve in that suction line actually shows up on the accumulator. So again, pretty easy to spot on the diagram. You know, if you're following it around, looking at all the little pieces and bits and things, that's pretty easy to find. If you see it buried in the middle of a rack, and if you've seen racks, you know, how much room is there for you to work? Yeah, none, right? Somebody wants it small, so we make it small, and these guys have to just deal with it. So need to be aware of that. This one is the, it has the two different pressures for serviceability. So we draw by color. So this pink section here would have that higher pressure rating. I think it was 80 bar. The blue side would be more at that 650 bar. So if I was going to service, I'm going to pump down, close this valve. I'm going to close that valve there. This all would be able to be operate at a higher pressure before it would release. I need to just open it up because this downside, all this stuff was at 650. That heat exchanger is at 650. We don't want to over pressurize that, maybe crack a plate on it. And this is the larger system, happens to have parallel compressors on it. It's at the ice rink. This is the one I was embarrassed at, wondering where was the booster compressor. There aren't any. A couple parallel compressors sitting there though. Again, this is where you wind up with having some administrative controls. And again, you need to look at drawings because you don't know necessarily where you might pop into an administrative control situation and see what you got going on with them. So that we're about at the end of our class today. Any questions?